Bismillahirrahmanirrahim. Welcome students to the online lecture of digital logic design. This is our first lecture and this will be dealing with the introduction about the course. First of all, we will discuss the basic information regarding this course. This course name is Digital Logic Design. Its code is triple E241. It's structured in such a way that it has 3 credits for the theory part and the 1 credit for the lab part. This will be the textbook that we are going to follow. This is the digital design with an introduction to Verilog HDL. This is the 5th edition. You can find the other editions too. This is just a very small difference between the edition, but I would still say that you should get this 5th edition. And then there are some reference books. If we use something from these books, I will explicitly mention you that these parts are from this book. We will discuss the few course learning objectives, that what will be the outcomes of this course, why we are studying this course. Basically, this course aims to familiarize the students with the basic concept of digital logic design. They are generally, we can categorize any given circuit or digital circuit, you can say, in a form of 2 types of circuits. One is the combinational one and the sequential. Other is the sequential one. We will study both of them. The teaching material that we will give you will help us to enable and understand the hardware and its design. We will also study some of the techniques related to the Boolean algebra and how we can utilize them in the digital logic design. These are basically, if you can divide the whole objective of the course in a form of a course learning outcome, that what would be the outcome at the end of the course. We generally define it in terms of CLOs and the PLOs, the program learning objectives. So for this course, the first CLO is concerned with the number systems, the basic arithmetics, and a little bit about the Boolean algebra. The second one involves the simplification of any given circuit. We will do this by using 2 techniques. One is the simple Boolean algebra, and the second one is a specific technique regarding to the digital logic course, which is known as the K-map. In the third one, we will design and implement 2 basic types of circuit. These are the combinational and the sequential circuits. Both of this part will be included in theory and lab. Specifically, the design part, it is included in both the theory part and the lab part. This is the list of experiment that you are going to perform in the lab part. You will also have a separate lab session in which you will get the details about these things, but these are generally the lab sessions which we follow in a digital design course. First, we will just try to understand that why we are studying this course. What if we don't study it, and we can we graduate without this course? Why is this course so important? Actually, this course is the basic building block of the future courses you will study, like computer organization, assembly language, computer architecture. This course forms the basic building blocks of any computer design system, or you can say a digital design system. So the whole concept is revolving around the digital system. First, we will try to understand what a digital system is, or how a digital system is different from an analog system, because mostly the system that we see in the real world domain are of analog type, or mostly the circuits you have seen by this course until now are mostly of analog in nature. So why is there a need of a digital system, and what are its importance or its advantages? Say for a Analog system, there are multiple example of different analog system. We start with a very basic example of a mercury thermometer. You must have seen this, a mercury thermometer. It is very commonly used in the hospitals, in homes. You can read the values here. From we read a red mercury values there. There's a scale there on the thermometer, and from that scale we see that what's the value of this mercury at that point, which will give us the temperature value. Generally, the mercury thermometer is considered, or this type of system is considered an continuous system, or we can say that an analog system. In this kind of analog system, we have all the values of the temperature measured. Say you can scale up into different values, and you can measure a very accurate value, that temperature is say 32.1 degree, or it is 32.15 degree, or it is 125 degree. So you can even go to a very minute decimal precision, and you can calculate the value of all these temperature at all the values of time. So if we have anything in which we have values at any point in the time, then we say that this system represents an analog system or a continuous time system. Simply, here is an example of a tape or radio system, just like a cassette player or a VCR, which records certain things. It records everything in continuous with the time. It doesn't miss any values. If you say on it a cassette for a certain time, it will keep on recording till you stop it. So it will record all the values between those two time instant. And similarly, just the human eye, because your human eye is a continuous viewer of the objects. You continuously view things. It doesn't stop at point unless you close your eyelid. Otherwise, it will keep on viewing different thing, and will be sending that images to your brain. On the other side, there is a complete different bird which we know as discrete system or digital system. In a digital system, we have a discrete set of values. First of all, what is a discrete set of values? Discrete set of values means that our system is divided into certain time scale. Mean that our system will read only values at specific time instant. Say it will read on 1 second, then it will read the next value on 2 second, and after that it will read on the 3 second, and then on the 4 second. So in a digital system, we don't have values at all intervals of time. We only have values at certain or specific interval of time, like 1, 2, 3. It could be second, it could be a millisecond. But we don't know what is the value between 1 and 2, or we don't know what's the value between 2 and 3, and similarly between 3 and 4. So as long as we keep that distance small between the two instances, we will get a very accurate value. There are many examples of it, just like the digital thermometer. Digital thermometer will only record a specific instant of temperature, rather than continuously reading the temperature all the time. It will only record the temperature when you press the save button. Similarly, a compact disc which has some data, or say you can just compare it with the example of the tape and radio player. We have a audio signal in here. In this case, the audio signal will be not in the continuous form like in a tape and radio player. It will be form of a discrete values, and when that computer or the system runs that things, it will always first use the information about the discrete values, and then it will play that audio file. Similarly, the digital camera. What does the camera do? It takes an image and just convert that images in form of a certain information or data, and store it in your computer. So you see that for all the digital system, all the things that are performed are based on the discrete values. They are no continuous signal. In fact, all of the system use these days, like say your PC, laptops, your mobile phone, or any other embedded device, all the systems are based on the digital systems. Their concept is that the first, because in real world all of the system are in analog form. the analog signals are converted into a digital form, and then we have the data values of these signals. We then perform different operations on that, and after performing that operation, we get the desired results. And in most of the cases, we have to also output that result back to the real world. So again, we convert that digital data back into the analog form. Say we have a two signal. This is a common example of an analog signal. That analog signal will always have values at all intervals of time, and it will have a continuous curve like this one. This is a continuous curve, and this it represents the example of an analog system. For representing this signal in a digital domain, what we do is we only represent the signal at specific instant of time. Here, if you see that the overall envelope of this curve is the same as this one. The shape doesn't change that much. Here you can say a staircase like plot for the digital system. How it is plotted in a way that after every certain time it reads the value. Say it reads the value here, then at time instant it will read the value at this point, then after that here, then after that here. So in the time it is only reading the value after a certain time instant, which are constant. Say the difference between the 0 and 1 is 1, and then 1 and 2 is also 1. So the distance between the any 2 points remains the same. So in this way we will read any digital signal. So this is an analog signal is a continuous signal on which we have value at all points of t, and while in the digital signal we will have a signal in which we have the values of a signal at only the specific time instances. Say 1, 2, 3, 4. We don't have any information what's the value between 1 and 2 and what's the value between 2 and 3. So what we do is we when we plot them, we use a specific type of circuit or a terminology you can say, which is known as the zero order hold. What it do is it keeps the value of the system constant till we get the new value. So what value was at, say it was time 0, it will remain constant till the value 1. So what value will have at time 1 will remain constant till we have value at time 2. So whatever the value at time 2 we have, it will remain constant till time 3. So we assume that in between the instances the value remains constant. And by observing these two graphs, you can clearly see that for any digital signal, if the time instance between the two points where we are reading the values is minimum, then we are much closer to this curve. If we are if the time distance between the two points or the sampling points is more or greater, then in that case we may have a loss of information. There are many benefits of the digital system. First of all, it's nowadays because we are available with a lot of resources regarding the digital design. So we can design a very cheap electronic circuit using the digital system. Although we can also say this for the analog term, but nowadays it is very convenient to have a electronic circuit based on the digital design. And the most important thing is that it is easier to calibrate and adjust, because in the analog system we don't have much flexibility with the system's parameter, or you can say in an analog system we may have a RC circuit or RLC circuit, and in that circuit we have to change the value of certain resistor and capacitor to adjust any values. But meanwhile in the digital system, the most of the processing is done by a computer or a microprocessor or a microcontroller. In that case we can always manipulate with the programming codes, and we can change how our system will behave. So it's very easier to adjust and calibrate the system in the digital domain. Secondly, because when we are dealing in the digital domain, we have the system in a form of a certain code. It could be a C language code, or it could be an assembly language code. In that case, we could always adjust the system to many other parameters, like say resistance to some noise, or removing rejecting some disturbances in the system. In this case, we can always apply the filters and the other things on the programming, and we will get our required output. Because this course is based on the building blocks of a basic embedded system or digital system. So first, we should know what are the basic components of a computer, and how and when we have to use them in a different part of a digital design course. So this is a common diagram of a basic structure of our say desktop PC or computer, normal computer. Uh, it consists of four, you can say, main parts. One is the input part. This input part is basically the method by which we can interface with our CPU or the central processing unit. The input devices that are related to this block includes, you can say, the keyboard, the mouse. These are basically the input devices, and you can always say that there are many other devices, like you can say the USB can act as a input devices. Then there is the PCI card. Then the sound card also act as an input devices. So these devices basically interface the outer world data with the computer. And how they are communicated with it, that the first all the values are digitized, and after that digitization, then we have the values in our central processing unit, and then our unit process them. Then another important thing is the memory. Always, whenever there is a digital system, there must be some memory system related to it. There must have some storage system involved in the system in it. We will also discuss this memory system in the next slide. Then we have a certain output system. The output unit function is to display a certain output, or give the information to the user that what processing the central processing unit have done. So in this case, the output, you can easily call them a monitor is an output device, or you can say that a printer is an output device. Similarly, just a oscilloscope, a digital oscilloscope is also an output device. So there are a lot of things which we can include in this part too. And then is the main central processing unit of this system. The main structure of the CPU involves a control unit and an arithmetic logic unit, which we also call the ALU part. In this course, basically, we will be building the basic blocks required to construct a control unit and an arithmetic logic unit. We will also try to design a arithmetic unit for a few bits, so that you can just have a know how a basic system operates. So this is our hardware, and this hardware is in the digital form. We have an input unit. By using this input unit, we will interface with our processor part, and after that processing, it will involve some memory unit, and after the results are generated, these results will be shown to the user through different output devices. Now we will discuss a little bit about the memory hierarchy, because in this course, in the end lectures, there is a small part in which we will discuss about the structure of the RAM and the ROM. We will like to have a few overlook that how a system memory works, or how the memory hierarchy of a computer system works. Say this is the CPU, or the central processing unit. Then we generally divide our memory, or categorize our memory in this kind of the part. The closest memory, which is to our CPU, is generally known as the cache. Cache itself is divided into, you can say, two parts. First is the L1 cache, and the second is the L2 cache. What does this L1 cache and the L2 cache do? It basically these give the CPU the most recent data it needs. All the recent data is stored in the L1 cache, and after that it is stored into the L2 cache. Basically, mostly the L1 cache is inside the chip of the processor, while the L2 cache exists on the motherboard. Then after these two caches, we have the RAM part. And in the RAM, we also use the temporary storage. The most recent things are also stored in the RAM part. And finally, the last one is the hard disk, or you generally say the magnetic disk we use in the system. In this memory hierarchy, if you see that the closest to the processor is the L1 and the L2 cache, because L1 cache lies generally inside the chip of the processor, while L2 cache is only mainly on the motherboard. While RAM is involved, is attached to a certain controller through a motherboard, while the system is also attached to a permanent hard disk or permanent storage hard disk or magnetic storage. In this hierarchy of the memory, if you see that if we follow from the CPU towards the hard disk, the size of the memory increases. L2 has always a very small size, mostly it's in KBs, while L2 cache it's just about few MBs mostly. Then we have the RAM, and the RAM is mostly in say you can say eight few GBs, 8 GBs or 16 GB in this ranges. While then we have the hard disk, and it's around about say the common convention that followed today is around 1 TB. So as you go further from away from the CPU or the processing units, the size of the memory increases. But on the other side, if you look at the speed of the communication, this tells basically the communication speed, that how it can communicate fast, how fast it can communicate with the CPU. So the first, the L1 cache and the L2 cache, they generally have the highest speed to communicate with the CPU, because the L1 cache it's inside the chip of the processor, so it's always very fast. It's in a few nanoseconds, you can say. And then we have the L2 cache. Its speed is after that, and then RAM is a bit slower than the cache, and in the last, the hard disk is the much slower than the RAM and the cache. So if we look at the speed, then in that case the L1 has the highest speed interface with the processor. The L2 will have the second highest, then RAM, and then the hard disk. Magnetic hard disk is very slow, but nowadays you have seen that SSD is here. So SSD is much more faster than the normal magnetic disk. So this is generally the memory hierarchy of any computer system. We will be studying this RAM and the ROM part, and we will be trying to construct a very basic module of the RAM and ROM in the end lectures. Now we will discuss a little bit about the logic levels, that how a digital system works, because whole of this course revolves around developing a hardware or designing a hardware, and that hardware that works on a digital signal. So first we have to know what a digital signal is, because most of the signal we will be dealing are of the binary logic nature. So it will have two state values, either it value will be 1 or it value will be 0. So based on this, how first we determine that what are the value, or how we can determine the logic level. So generally the logic level is determined in a way that if the value of the point that which we are measuring, it's say its value is between 0 to 1 volt, then we can categorize it as a 0 volt. So we will give it the name the logic 0. So any value between 0 to 1 volt will be named as logic 0, while any value between 3 to 4 or 3 to 5 volts will be named as the logic level 1. Because we have put the specific values here, that minimum value of 0 volt and maximum value is 1 volt for our logic level 0, and similarly for the logic level 1 we have a minimum value of 3 volt and the maximum value of 4 volt. You can see that we haven't put a specific value, that say 3.5 volt is equal to logic level 1 and 0 volt or 1 volt is equal to logic level 0. This is because we give the system certain room, because of any interferences, any noise or any disturbance could cause the system values to vary. So we give it a range of values. So if the system values lie between 3 to 4 volt, then we will say that it represents logic level 1, while if we have a value of system at around between 0 and 1 volt, then we will give it as logic level 0. In general terms, you can also see that we will be using in the certain hardware and ICs, you will see that Generally, logic level 0 is considered for any value less than 2.5 volts, and any value between 2.5 to 5 volt is considered as a logic level 1. There are different standards which you will be studying in the lab part. This was just the basic introduction about the course, that what we will be studying in this course, what kind of things we will be dealing with. Because this system is the digital logic design, it's mainly focused on designing the hardware part of the system. So it's very important to know the why we are studying this course and what importance it is, because you are, whether you are a computer engineering or you are a computer scientist, in both cases you have to integrate a different system with your certain software. So you can only design a hardware and software system combinedly if you have the knowledge of both. So that's why this course is very important in terms of the architecture, understanding and design of a digital design. For the reading, just do read the preface of the book. Kindly do follow the book. Whatever topics I will be telling you from the book, kindly do read these pages from the book. It will also give you a very good introduction about the course. Thank you.